So far we have seen how we can model various sequential and combinational circuits using Verilog language. And you may note the kind of variables that we have used for most of these examples were either single bit variables or it was a vector. Well, in some very specific cases we use two dimensional matrices or arrays. Now, in this lecture and the next, we shall be primarily focusing on how to model some specific kinds of two dimensional data elements. In this lecture, we shall be looking at how to model memory elements. Now, conceptually speaking, a memory element can be regarded as a two dimensional array of storage cells. For example, let us say if I talk about a let us say 4 kilobyte memory chip or a memory cell, what does this mean? So, it is a box inside which there is storage space for 4 kilobytes of data. Byte means there are 8 data lines available to me, and 4K means there are 2 to the power 12 is 4K. So, there are 12 address lines available to access one of the memory words, and the size of the memory word is 8 bits. Okay? Fine. So, how we can declare such a memory cell as an array, and how we can use it in a Verilog code, we shall be seeing through this lecture. Okay. So, the question is how to model memory. Now, the first thing I would like to say is that, well, when you are doing a professional design which will be finally targeted to a hardware. So, when your aim is to synthesize the hardware into an ASIC or an FPGA, then the kind of memory blocks that we use are not exactly what we shall be talking about now. There we will have to pick up some existing memory cells from a library. For instance, when you are using some kind of FPGA, then there are some pre-designed memory cells available in the library. You can pick them up, you can put them in your design, and you can create whatever size memory you need. Similarly, for an ASIC, normally the way memory elements are laid out and fabricated are quite different from the way normal gates are laid out. That is why the layout of a memory is entirely separate, and they are typically available as a prefabricated element in the library. Okay? Fine. So, that is what the first point says, that in a real design where your target is to synthesis, memory will be typically included by instantiating some existing module from a library. Okay. Now, in the examples that we shall be showing today, that as an alternative we can also model memories using a two dimensional array. Now, you see, memory conceptually consists of a number of words, each word consists of a number of bits. So, each word we can regard as some kind of a register. So, a memory array can be regarded as an array of registers, where each register has a particular width, number of bits. Okay? So, memories can be modeled as an array of register variables. Of course, this is a behavioral model and we shall be looking into this, and this is quite useful for simulation purposes to check whether the rest of your design is correct or not, right. And also for memories which are relatively smaller in size, there also you can use this kind of behavioral model. But for larger memories, as I said, you have to take some module from a library, design library. Fine. So, a very simple example. So, a memory module can be declared as follows. So, it is a registered array. Reg 720 mem 01223 means there are 1024 memory words and each of the word is an 8-bit vector, right. So, each memory word will be 8 bits and to access the individual memory words, there are 1024 of them, we will have to just access them using the array notation mem0, mem1 up to mem1023, right. So, just one very simple example how we can initialize some memory content, some particular addresses in memory in some data. So, this is the same declaration. Well, in an initial block, just an example. So, I have written mem0 equal to this will actually be bit, this B is missing. Okay. So, this is an 8-bit number 0100 1100, this is stored in memory address 0 and mem4 means this all 0 pattern, this is stored in memory location 4. So, this is how we can initialize a memory word inside a Verilog module. Similarly, you can access it as follows mem0, mem1, mem2 on the right hand side, same way. Talking about initializing memory in general, there are some other methods available that are quite useful for simulation. Like you can read some data patterns from a file in the disk. Like suppose I have a large memory where there are a large number of memory locations. Just writing the way I just showed, just assigning values to the different addresses, that way your code will become very long. If there are 1000 memory locations, there will be 1000 lines of the code. But as an alternative, what you can do, you can store the data that you want to load in the memory in a file beforehand, and then there is a function call. Using that function, you can load that entire contents from that file into that defined 2-dimensional memory array. Okay. So, there are two functions available and these functions are useful for simulation, particularly in the test benches. These two functions are read memory binary and read memory hexadecimal. So, in the first function, the data will be stored in the files in binary format, in 0-1 format, while in the second one they will be stored in hexadecimal format. So, you see there are 4 parameters. First one is the name of the file from where you have to read, then the name of the array memory where you want to store, and start address and stop address, they indicate that, well, I mean you may not be wanting to initialize the whole of the memory, maybe only a part of the memory. So, the starting and the ending address you can specify as the third and fourth arguments. Now, if you omit this third and fourth arguments, then the entire memory will be read, right. So, just a couple of examples. So, here we are saying read memory in hexadecimal from this file into this variable mem, mem is the memory. Since we have not specified start and end, so here we will store the entire contents of the 1024 locations from the file. Here you see there is another example where we have specified start and end, but start is greater than end, start is 200, end is 50. So, here memory will be initialized by reading from the file starting from address 200 onward, 200, then 199, then 198, 197 down up to 50. But you can specify the other way around also, 50 comma 200 you can also write. In that case, it will start from address 500 and go up to 200, right. So, this is how we can initialize a memory, define memory from data stored in a file. Okay, here there are some examples. This is an example module declaration where we have used a single port RAM with synchronous read write. So, what does this mean? This means we are trying to design a random access memory which can be read and written both. So, here I am assuming that there are some address lines which we call as ADDR, there are some data lines which we are assuming to be bidirectional. That means, I can either write into the RAM or read from the RAM over the same lines. Now, in addition there are some control signals, like there is a read signal, there is a write signal, there is a chip select signal, and of course, there will be a clock signal, because it is synchronous, there has to be a clock also. Reading and writing has to be in synchronism with the clock. Now, here the memory is, the data bus is bidirectional, okay? It can be read and also it can be written. That is why you see in the declaration, this data has been declared as in out. Well, this is a data type which you have not seen so far. The main reason is that it is best avoided, because in out, the way it is handled by the simulators and the synthesizers is not consistent. It varies quite significantly from one system to the other. So, it is a good suggestion to the designer, you should avoid in out where possible. Okay. But in this example, I am showing how in out can be used. You see, in out is by default of type wire. Okay. So, this is my memory. So, again 1 kilobyte 1024 into 8, and I am using a variable d out where I want to write it, and from d out to the memory I am using an assign statement. This assign data bus. So, whenever I chip select is there and read is there. So, from d out the data will come to this data bus data, and if they are not enabled, then data will be tri-stated 8 Z. Okay. And it is synchronous operation in terms of read write. Posage clock, if you are selecting the chip, write is active but not read, that means you are doing to write, data is written into mem ADDR, and if it is read and not write, then you are reading into D out. Now, you see, you cannot directly read into data, because I said this in out by definition is a wire, and inside a procedural block you cannot have a wire variable on the left hand side. That is why I defined a temporary reg variable D out, assigned it there, and in an assign statement from D out I put it back to data, right. So, this is one way of specifying a single port RAM with synchronous read and write. With slight modification, you can make asynchronous read and write. Like here you see, so in the earlier design, you are using the positive edge of the clock for doing the reading and writing. But for asynchronous, here we are not using clock, the clock signal is not there anymore, only address data, read, write and chip select. So, the other declarations are similar. Now, you see here the two always blocks are activated by change in any one of the input variables, either address changes or data changes or read, write, chip select. The rest is the same. Okay. So, synchronous and asynchronous, both memory module definitions are very similar. So, in one case we are using the clock edge to synchronize my reading and writing, and in the other case there is no clock, whenever the signals changes. So, in accordance to that we will be doing either reading or writing depending on whether read is active or write is active. Okay? Fine. Now, as I said, this in out is not a very good way of using it in a module, we shall see it a little later. But first let us see, so how we can model a memory where you are not writing, only reading. That means, it can be either be a read only memory or it can be a erasable programmable read only memory, EEPROM. So, in a ROM or a EEPROM, we are assuming that we are storing some data in the memory that is fixed, we can only read from there. Okay. So, for a ROM, when you model a ROM or a EEPROM, you need not use that kind of an array notation where you are storing and reading like that. Rather, you can use a case statement. So, here we have used a very small example. Let us assume that my address is 3 bits. So, here we have taken a very small example. Let us say I have a ROM, the address lines are 3 bit address. So, inside the ROM there will be 8 locations, and each locations I am assuming they are 8 bits in size. So, what I do, I just specify like a lookup table, there will be 8 locations. So, I store the 8 bit values, and depending on the address, so one of these will be selected, address 0, 1, 2 up to 7, right. This is done by using a case statement. So, you see here there is a always block, this is activated when either address or there is a signal called read enable, because from a ROM you can only read, you cannot write, and chip select. So, when means any of them these are active, then you start the reading. There is a case ADDR, the address can be 0, 1 up to 7, and you have stored some fixed data inside. So, if you have given address equal to 0, data equal to 22, if it is 1, data equal to 45, and so on. There will be 8 lines like this. So, this is how you typically model a ROM or a EEPROM, where you do not change the data, data is fixed, that is why you are using a fixed case statement, right. Fine. Now, the point that I was making, this in out is a data type which is best avoided, because as I said, some simulation or synthesis tools can give inconsistent behavior. So, the experienced designer says that do not use in out data type inside a Verilog code. But does that mean that I will not use any bidirectional lines in my hardware? You see, there are many instances where I do need bidirectional lines. Memory is a very good example. So, I will use bidirectional lines, but I will not use in out data type in my Verilog module, in my Verilog code. Okay. Let us see how. So, what we do? We keep the data input and data output lines separate, and then we will see how we can make it bidirectional. First, let us do it in one step. First step says data input and output lines are kept separate. So, how does it look like? It is something like this. So, I have a memory, a RAM. So, I have my address, data in is separate, data out are separate, 2 set of data buses, and read. Okay, there is no separate read line. What is meant is write is like a read write both. If write signal is high, it means write, if write signal is low, it means read. So, it is like a write slash read bar. Okay. So, I am just assuming that this kind of a signal is there. So, let us see how the module definition will look like. So, here we have used parameters to make our specification general. So, we have assumed address size is 10, it is a 10 bit address, which means 1k words. Word size is 8, means 1 byte per location, and of course, memory size will be 1024, 2 to the power 10. So, there are the parameters are data out, data in, these are the arguments, address, write, and chip select. So, we have declared the variables. The ADDR is of size 0 up to address size minus 1, 10. Data in it is an input, again 0 up to word size minus 1, word size is 8. And similarly, for the output, data out is an output, that is this is an output. So, here the size is again word size minus 1, 8, and write and chip select are single bit inputs, and here we have defined our memory. This is number of bits per word 0 up to word size minus 1, and this is the total number of memory locations, it is 1024. Now, the way we have implemented is very simple. Writing we are doing in the always block. So, whenever write or chip select, that means this changes, then inside it you check if write equal to 1, then only you write mem addr equal to data in. Since mem is of type reg, there is no problem, you can write it, but for reading the data we are not using always block, we are using an assign statement, because data out is declared just an output which is wire, it is not reg. So, mem addr equal to data out. So, from data out it will always be reading out, but whenever there is a write active, data in will be written inside, right. This is the specification of the memory module here. Now, let us see how we can make it bidirectional. You see, this much we have implemented. We have implemented a memory module with separate data out and data in. Now, what you do? We use two sets of tri-state buffers. So, one we activate by write, other we activate by read. Now, in the previous example there was no separate read signal. So, we can activate it by write bar. So, when write is 0, and on the other side the two tri-state buffers are connected together and you have a single bus. So, you enable either this or this, both of them are not enabled together. So, when you are activating write, this is off, and whatever is coming here, this will go through this into the data in, and whenever you are activating read, this is off, this is on. So, whatever is coming out of data out, that will be coming via this. Okay. So, now you see in the module you are not declaring anything as in out, but by using tri-state buffer you have implemented a bidirectional bus. Sometimes you are moving here, sometimes you are moving here. So, how you can declare? You can declare it very simply like this. Let us say this variable, let us call it bus. Here we define it as tri, this is a tri-state. Data out and data in are of type wires, let us say, and we have two assign statements. Assign bus equal to when read is active. When read is active, data out will go to bus, data out will go to bus, and otherwise it is tri-state, this buffer is tri-state. And in the other assign statement, data in equal to, depending on write, bus will go in, or if write is not active, then tri-state. So, just a normal memory module with separate input and output data and these kind of tri-state bus and enabling them will make the overall thing a bidirectional data bus enabled. Okay. Fine. Now, just a simple test bench we are writing just to test this RAM3 module which we just wrote. Okay. So, we are just showing a simple test bench. So, these are the two parts of the test bench. Let us see. So, here we have instantiated the memory, data out, data in, address, write and select. So, here this is wire, there is a typo, wire. Okay. So, this address is of type reg, data out which will be coming out of the RAM, this is of wire, data in will also go inside. So, that has to be of type reg, write and select you have to activate, chip select and write, those are also type reg. And we have defined two integers in addition, k and myseed, for the purpose of writing the test bench. Now, here you see what we do in the first initial block, we initialize the whole memory. How you do? In a for loop, k equal to 0 up to k equal to 1023, we go in a loop, and what you store? We store k plus k modulo 256. So, if the address, if k is 0, 0 plus 0 is 0. So, if k is 1, 1 plus 1 is 2, If k is 10, 10 plus 10 is 20. If k is 100, 100 plus 100 is 200. If k is 200, 200 plus 200 is 400 modulo 156. Divide by 156 and take the remainder. So, it will be 144. Like that data will get stored. This is the initialization part. So, when you store something in the data, you activate read equal to 0, write 1 and select 1. So, that this data will get written into the corresponding memory location. So, this gets written. So, after this, now here you repeat 20 times. Just I am randomly selecting 20 addresses and I am reading them out and seeing what is there. So, I am just calling the random number with this seed mod 1024. So, an address in the range 1 up to 1023 will be generated, that is my address. Write is 0, that means I want to read, select is 1, I display address, data. So, whatever is coming out. So, if I simulate it, I see that my output is coming like this. So, repeat 20, there will be 20 lines generated. These will be the random addresses, like the smaller one you check, address is 21. So, what does address 21 contain? K plus k, so which is 42. So, the others one also 193. So, 193 is how much? 193 multiplied by 2, just let us check. 193 multiplied by 2 is 386. Now, 386 mod 256 means what? Divide by 256 and take the remainder. So, basically minus 256, which means 130. So, you see in location here 193, data is 130. So, accordingly you can verify the operation. Now, here there is one mistake that I see which I have missed out. Here I have not put the address, you will have to put another line here. Here you will have to put address equal to k. This is missing, because where you will be writing? You will be writing it into address k, right. Data you are calculating, you are storing it into data. Right, and this write and selector activated, this will be data in actually, data in, yeah, fine. So, you have declared it as data in. So, data in will be getting this data, address will be k, and then you write 1, select 1, it will be written, okay, like this. So, with this we come to the end of this lecture. So, in this lecture we have basically seen how we can model some memory devices as a 2-dimensional array, as an array of registers, and at least from the simulation point of view, wherever you need memory elements in a larger design, you can implement the memory systems like this. So, we shall see some examples later also, where you use these kind of memories in a larger system, and you can simulate them and see how it works. And again I had said, for smaller memory systems, even the synthesis tool will be able to synthesize the memory, but it will not be very efficient in terms of hardware. They will be implementing, the synthesis tool will be implementing the hardware in terms of flip flops and arrays of flip flops, but an actual memory chip, the way it is constructed, it is much more compact, much more efficient in terms of number of transistors required per cell, per storage cell. Okay. Thank you.